Welcome to this explainer on the art of data analysis. If you've ever felt completely overwhelmed by statistical jargon, you're definitely in the right place. Today, we're going to clear up some of the most confusing concepts in statistics, like the crucial difference between a sample distribution and a sampling distribution. And we're going to do it using something incredibly simple and honestly pretty relatable, a regular old box of raisin cereal. Okay, let's dive right into this.
Picture this. You're holding a box of raisin cereal, and the label proudly screams, "Now with more raisins." It naturally begs a pretty obvious question, right? Exactly how many raisins are typically in a single cup of this stuff? Now sure, you could rip open every box in a massive warehouse shipment and count every single raisin. But come on, that is practically impossible. Instead, we have to rely on a bit of magic, taking a smaller part to understand the whole. We need a sample.
All right, so here's our roadmap for today. We're going to tackle the cereal box question, look at sample versus sampling, and check out the sample distribution. Then, we'll dive into the sampling distribution shift, navigate deviation versus error, and wrap it all up with the art of data analysis. Okay, part 1. The cereal box question, approaching the truth. So when we ask about the typical number of raisins, that word typical is a massive clue that we need statistics. And this brilliantly illustrates our ultimate goal. What you see on the left is the population, which is all possible 1-cup servings from that entire cereal box. That holds our true mean, the universal truth, which we represent by the Greek letter mu. But since we literally can't measure the entire population, we do the next best thing and look to the right. We take a sample. Say 30 random cups of cereal from that huge shipment, and we actually count those. We calculate the sample mean, x bar, to estimate that hidden universal truth. We desperately need a sample because it's our only practical vehicle for getting as close to the truth as possible.
Moving on to part 2. Sample versus sampling. Language matters.
Before we even look at any numbers, we absolutely have to get our vocabulary straight. Distinguishing these two terms is literally the foundation of being statistically literate. Sample and sampling sound super similar, right? But mixing them up is a classic rookie mistake. A sample is a thing. It's the actual physical data sitting right in front of you, like our 30 individual cups of cereal. Sampling, though, is an action. That ing at the end, it points to the process. It's the physical act of shaking the box, dipping the cup in, and counting the raisins. So just remember, the sample is what we get, and sampling is exactly how we get it.
Part 3. The sample distribution, the lumpy reality.
Let's zoom way in on the micro-reality of that one single sample of 30 cups we just scooped up. What you're seeing here is the frequency distribution of our observed raisin counts. Along the bottom, you've got the number of raisins in a cup, and the height of the bars shows how many cups actually had that exact amount. Now look at the shape. It is definitely not a perfect, beautiful bell curve, is it? It's lumpy, kind of skewed, totally uneven. I mean, some cups only had 3 raisins, and one lucky cup somehow had 20. So the crucial takeaway here is that a sample distribution, which just describes the values inside one single sample, does not have to be normal. In the real world, observed data is often pretty messy. And since our cups don't magically all have the exact same number of raisins, we need a way to measure that lumpy, uneven spread. Enter standard deviation. Now, before your eyes glaze over at the thought of math, let's just talk about the concept. Standard deviation just answers one simple question. How much do individual cups typically vary from our sample mean? A really small standard deviation means the cups are practically clones of each other. A large one, it means your raisin counts are just completely all over the place.
Okay, let's briefly look under the hood at the math process here. To find this standard deviation, which we just call S, we calculate the variance of each individual cup from our sample mean. We square those differences so everything turns positive, add them all together, and then divide by the number of cups minus 1 to find the average variance. Finally, we take the square root to get back into our everyday raisin units. Honestly, it's just a fancy mathematical way of finding the typical spread inside one single sample.
All right, part 4. The sampling distribution shift, the big statistical surprise.
So, let's shift gears from the micro level of one single sample to a huge macro-theoretical view of thousands of samples. Imagine we have a bunch of different groups of people, and every group scoops their own 30 cups from that exact same cereal shipment. Group 1 calculates a mean of 8.9 raisins. Group 2 gets 10.2. Group 3, 9.4. Now, the cereal itself didn't magically change. What changed were the samples. This natural bounce from sample to sample is called sampling variability. Basically, every single time you scoop a new sample, you're going to get a slightly different average. It's just a fact of life.
And that brings us to the big plot twist. What happens if we take thousands of theoretical samples of 30 cups, calculate the mean for every single one of those samples, and then graph all of those means together? We get this, a sampling distribution. Notice we aren't plotting individual cups anymore, we are plotting sample means. And check out that shape. That lumpy, weird reality of our single sample has completely smoothed out into this beautiful, highly predictable bell curve.
This incredible phenomenon actually has a name. It's the central limit theorem, and it tells us that under reasonable conditions, as your sample size gets larger, the sampling distribution of your sample means becomes approximately normal. Why does that happen? Because while individual cups of cereal might be wildly unpredictable, the averages of repeated large samples behave incredibly beautifully. Messy individual data naturally settles into predictable patterns when you average repeated large samples.
Which leads us to part 5, deviation versus error. Navigating uncertainty.
Now that we've got this incredibly useful, super smooth sampling distribution, we kind of need a way to measure its spread, right? Just like standard deviation measured the spread of the actual cups, standard error measures the spread of the sample means. And the math behind standard error is surprisingly simple. You just take your sample's standard deviation, that S we talked about earlier, and you divide it by the square root of your sample size, n. This standard error describes exactly how much sample means vary from sample to sample. Think of it as our ultimate measure of uncertainty.
Putting these two concepts head-to-head is absolutely vital for true statistical literacy. Listen, standard deviation lives in a sample distribution. It asks, hey, how variable are these individual cups? Standard error, on the other hand, lives in a sampling distribution. It asks, how reliable is this sample mean as an estimate of the truth? So one measures the actual things and the other measures the statistics.
And honestly, this is exactly why we need a decently sized sample, like 30 cups, instead of just, say, 2. If you only sample 2 cups, one freak scoop of 20 raisins is going to drag your whole average way, way up. Your sample means will just jump wildly all over the place, which means a really high standard error. But with 30 cups, those unusual highs and lows naturally balance each other out. As your sample size grows, the standard error physically shrinks, which makes your sample mean a much, much more stable and reliable estimate of the actual truth.
Finally, part 6, the art of data analysis, becoming statistically literate.
We've talked a whole lot about the math today, but what does it actually mean to be statistically literate in the real world? Well, it means knowing that beautiful math is completely useless if your process is bad. I mean, if all the raisins settled at the bottom of the box during shipping and you only scoop from the very top, your data would be fundamentally flawed from the get-go. The art of data analysis requires a really rigorous sampling method, gently shaking the box, using the exact same measuring cup every time, scooping from different areas. How you sample is literally just as important as the data you collect. And this right here perfectly captures our entire journey today. We desperately want to know the true population mean, but we can only ever access a sample. But by understanding standard error and the magic of the sampling distribution, we can actually put a number on our uncertainty. We use that calculated uncertainty as a bridge. It allows us to take our messy, imperfect sample and confidently estimate the hidden truth of the entire population.
It all boils down to this really beautiful quote: statistics helps us reason from a smaller part to a larger whole. We started out with a lumpy, imperfect sample of 30 cups of cereal. But because we understood the difference between the data in our hands and the theoretical distribution of thousands of samples, we unlocked the power to estimate the truth of an entire massive shipment. So, I'm going to leave you with this thought. If a single, careful scoop, analyzed with the right statistical tools, can unlock the truth of an entire universe of cereal, what other hidden facts in your business or your life or our world are just waiting for you to sample? Stay curious, keep exploring your data, and I will see you in the next explainer.